Today's class will prove some theorems on vector space. Here is a theorem which states V be the vector space with the basis consisting of n elements, then any n plus 1 elements of vector space V are linearly dependent. You can prove this in different ways. You can prove by using induction on number of elements, that is n. I'll take up the other way. If I have n plus 1 elements, any n plus 1 vectors in a vector space V. So let me take the vectors, n plus 1 vectors, v1, v2, like that, n plus 1. Let v1, v2, dash dash vn plus 1 be any n plus 1 vectors in my vector space V. Okay, suppose first n vectors are linearly dependent, then suppose first n elements, okay, v1, v2, vn are linearly dependent, then there exists some scalars, say a1, a2, an from the field F. Not all of them are 0, okay, such that there is a trivial relation, that is a1 v1 plus a2 v2 dash 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 an vn equal to 0. Okay, I'm considering first n elements as linearly dependent. Okay, and I want to prove when I take n plus 1 element, then the whole set becomes linearly dependent. That I have to show. So I'm taking first n elements as linearly dependent. Okay, when they are linearly dependent, then there exists some scalars in such a way that this is the trivial relation. You are getting not all ai's are equal to 0. So this can be rewritten as a1 v1 plus a2 v2 dash 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 an vn, and I can even write 0 into vn plus 1, which is equal to 0. Again, here also not all ai's are equal to 0. Hence, what I can say, this v1, v2, v3 dash dash vn plus 1 elements are linearly dependent. See, if all ai's are equal to 0, then only they are linearly independent. Here not all are equal to 0, just the nth plus 1 scalar is 0, that is an plus 1 is 0, only one element is 0. Maybe some are 0 but not all are 0, right? Therefore I can say that v1, v2 dash dash vn plus 1 elements are linearly dependent. This is, I have taken first n elements as linearly dependent, and I have shown n plus 1th element along with this set becomes linearly dependent. Now what I'll do is, I'll take these n plus 1 elements as these n elements as linearly independent, and I'll add one more element, that is n plus 1th element, and I'll show they are linearly dependent. Okay, so let the vectors v1, v2 dash dash vn are linearly independent. Initially I had taken they are linearly dependent. Now I'll take these n elements as linearly independent, and then when they are linearly independent and they form a basis, okay, this form a basis, that means they span the vector space V, When they are linearly independent, they form a basis. It means that they span the vector space V. So I have taken n plus 1 element, so this n plus 1th element is in my vector space V, and these are the vectors which span the vector space V. Therefore this n plus 1th element is generated by using these vectors. Okay, so I can write n plus 1 Vn plus 1 belongs to V is in their span as well, so that there exists some scalars, say b1, b2, bn belongs to the field F, such that, say, this n plus 1th element is generated by using these vectors with the scalars b1, b2 dash dash. Okay, which implies b1 v1 plus b2 v2 dash dash bn vn plus minus 1 into vn plus 1, which is equal to 0. What does it imply? See, not all scalars are 0 because they are linearly independent. Therefore, these scalars are not all of them are 0 when I take n plus 1th element, bn plus 1 when I take, this one is not equal to 0. Therefore, I can say these vectors v1, v2, vn plus 1 are linearly dependent. v1, v2, v3 dash dash vn plus 1 are linearly dependent. Okay, this proof you can even do it by taking induction on n. You take first initially n equal to 1, and that means the vector space has a basis with only one element. Okay, and you take two vectors in a vector space V, and either one of them, one vector should be equal to 0, like that. You can prove this by using induction on n also. I have taken some other method which is quite easy. Next is corollary to this theorem. If I have any two bases of vector space V, then the number of elements in those bases are same. Okay, any two bases of V will have the same number of elements. It's very easy. If I have a vector space V and one basis is this, say E1, E2, like that, En, and another basis is F1, F2, Fm, say. Okay, one basis have got n elements, another one has m elements. I have to prove m equal to n. Suppose if I consider this as set of linearly independent vectors and this as a basis. Okay, if I consider this as a linearly independent set of vectors with m elements, then the number of this number of elements in this basis is m, which must be less than or equal to number of elements of a basis. See, since F1, F2, Fm are linearly independent and E1, E2, En is a basis, if I consider this condition as basis of V, then I can say this number of elements which are linearly independent, this number of elements must be either equal to n or less than or equal to n, because these n elements form a basis. Therefore, m must be less than or equal to n. This is if I consider this as linearly independent vectors and this as basis. In fact, both are basis. I'll just I just considered this as set of linearly independent vectors and this as basis. If I consider this as a set of linearly independent vectors and this as a basis, then n must be less than or equal to m. So from these two you can say that m equal to n. That means two bases, they have same number of elements. Next is, say, remember one thing, if I say dimension of a vector space, then it means that number of elements in the basis. Dimension of a vector space is nothing but number of elements in its basis. And if a vector space has 2 or 3 bases, then the number of elements in all the 3 bases are equal. Okay, that is the point, you should keep it in mind. Let us prove next theorem. It says let V be a vector space of dimension n, then any set of n linearly independent elements of V form a basis of V. Let us prove this. I'll take n elements which are linearly independent vectors. Okay, so let V1, V2 dash dash Vn, they are linearly independent vectors of a vector space V. Then for any vector, say some V belongs to the vector space V, then the set of vectors V, V1, V2 dash dash Vn becomes linearly dependent. Okay, since they are linearly independent, some vector I am considering from a vector space V, and if I take up this set, then they form linearly dependent. Means there exists a non-trivial relation such that, say, A1 V1 A2 V2 dash 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 AN Vn. Say for this vector I'll write the scalar as simply AV equal to 0. Means since I know that they are linearly dependent, then I can write this non-trivial relation. Since I know that V1, V2, Vn, they are linearly independent, and not this A is equal to 0. Therefore, I can write V in terms of linear combination of these vectors, right? Since V1, V2 dash dash Vn are linearly independent and the scalar A is not equal to 0, I can write the vector V as minus A inverse of this vectors, this linear combination A1 V1 plus A2 V2 dash 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 AN Vn. Okay, this V is written like this now. What does it imply? This vector can be written in terms of linear combination of these vectors, right? So these vectors form a generating set. Okay, this V1, V2, Vn, their linear combination giving me the new vector V. Okay, therefore I can say that these vector form a basis. Here I have taken some vector. After adding that vector to this linearly independent set, I am getting a linearly dependent set. So now this new vector can be written in terms of linear combination of these vectors. Therefore, I can say that these vectors form a basis. They form a generating set. Therefore, I can say V1, V2 dash dash Vn. this is any linearly independent set of elements, they are forming form a basis. Form a basis of P.